So this time we're going to discuss light again as a whole and whether or not it is a wave or a particle. It's a question that's been asked throughout the ages and argued back and forth. As we've been doing ray tracing and ray optics, we have been assuming that light is consisting of particles called photons that are infinitesimally small objects that travel in straight lines until they run into something else. And that explains a lot of phenomena, and this is why Newton, who was one of the original people to come up with this idea of particles being light, it's why he was able to explain some of the things so well that we have in our endeavors, such as light coming in and bending, refracting, and reflecting off of a surface. Eventually, though, there was a guy named Thomas Young who came up with an experiment that simply could not be explained by particles anymore. All he did was he had sunlight blocked by a screen and then projected light onto a wall that wasn't blocked by the screen. And what I mean by that is he punched two small holes into the screen, and then he looked down the wall to see what happened. And to his amazement, instead of seeing a bright spot here that eventually faded away, and a bright spot here that faded away, as you might expect in the ray optics or particle case, he saw something entirely different. I'm going to have to redraw my wall now. So he saw a bright spot in the middle, in between these two slits, then a region of darkness, and then a less bright spot, and then another region of darkness, and then another bright spot on both sides, dimming as it went out, but having these dark spaces in between, which we now call fringes. Generally, when you see these bands of light, dark, we call them fringes. And Young eventually said, well, the only way this makes sense is if light is a wave. And what he meant by that is if light is truly a wave coming out of this slit and light is a wave coming out of this slit, then it will look like the following. And he actually drew this out in his publication. Will look like a wave coming out, being emitted or emanating from the slit. I'm going to draw this in pink. So this is the other wave coming from the other slit. And you can see now that the two waves eventually run into each other and interact quite a bit. And this interaction is what causes the fringes. Essentially, the two waves interfere with each other. And what that means is if you look at a particular spot between the two slits, if the distance between the two slits is the same, then the waves will have traveled the same distance and look the same. So you will have two waves at the same spot that look identical. And since the waves add on top of each other, you can simply take any two light waves you have and add them together. That's called superposition. These light waves are superimposable. They're addable. You just get the sum of the two, which is a wave that is twice as big. But if you look at a different spot on the screen where the light has to travel much further from one of the slits than the other, then the waves will look different. And in the most extreme case, you'll have wave number one looking like this, and because the other wave has traveled a different distance, it could look the exact opposite. And if you add these two together, you get nothing, or no wave at all. In this case, the most extreme possibility of constructive interference between two identical waves is just a wave that's twice as big, and the other extreme is getting no wave at all, 2 times or 0 times, or anything in between. And this is called interference, when we have two waves, or more than two, adding together to cause bright, dark fringes. So for a very long time everybody said, well, this can only be explained by a wave, therefore light is a wave. What a wave of what, though, is what people were still confused about and didn't have a good explanation for. For a long time they said light is a wave that is really just a disturbance in what they called the ether. It's some material that permeates throughout the universe that light is able to use in order to travel through it and be a wave. Just like when you use a sound wave to talk to somebody else, you're actually using the air, which compresses and relaxes in a wave-like fashion. It's the medium in which the wave propagates. In this case, they said ether is the medium for light. But in a famous experiment carried out by a man named Michelson, he actually built an interferometer, which is something that has a light source, and he had a piece of glass to split the light into 2 directions, and had mirrors on either sides of that arm, which then combined and came out to some detection source, possibly a screen or an eye, what have you. And so they built this interferometer, which just splits the light into 2 and interferes them. And the interference that you see is dependent on the difference in travel length between the 2 arms. That changes what the wave looks like when the 2 waves come back together and interfere, whether or not you would get a bright spot or a dark spot. And their reasoning was that as the Earth travels around the Sun, it is orbiting in a circle, and if there is an ether and in space allowing light to use as propagating, then when the Earth is traveling in this direction, and that should produce a different result than when the Earth is traveling in this direction. Essentially, you just need to wait half a year for the Earth to be traveling in a different direction through space, for it to be traveling in the opposite direction through the ether. And when you do that, you would expect that because light is in the ether, you would expect some shift in one of these arms as you're traveling through space in the opposite direction that you were 6 months ago. Anyway, they found that there was no difference whatsoever between the 2 measurements they made 6 months apart. It's one of the most famous experiments that failed because it gave a very important lesson. Normally you think of experiments failing as a bad thing, but you have to remember in science, being able to disprove things is just as important as being able to prove something right, because from this we learned a very valuable lesson, that there is no ether. I'm going to write this out so that there's no confusion. There is no ether, and it is because of the Michelson experiment failure that we know this. This experiment was carried out dozens of times afterwards just to make absolutely sure, and we know this for a fact. Light does not have some special medium with which it propagates when it's a wave. So how can light be a wave then? There's nothing for it to travel through. Well, that was a bit perplexing for a while, until a guy named Maxwell came along, and he was playing around with equations for electricity and magnetism. just equations that had been developed over the ages to explain both of these. Electrons going through a wire, current, and magnets. Not quite what you would expect in terms of someone who is dealing with light. Well, he didn't realize he was dealing with light at the time. He was just working with these equations. And he eventually asked, what if I have an electric wave and a magnetic wave that are working off of each other, that cause each other to oscillate and move? What would that wave look like, and what would it do? I'm going to try to draw it. I really hope I'm successful, because it'll be very difficult to see if I don't draw it very well. The red wave in this case would be the magnetic wave that is coming in and out of the screen, and the electric wave is the yellow wave I've drawn that is moving, that is oscillating up and down. When the two waves are perpendicular to each other like this, but also feeding off of each other, ebbing and flowing exactly in phase with each other like this, Maxwell discovered something very, very interesting, because this wave actually tends to propagate or move in a certain direction. It goes. It does not stand still. Many waves that you solve for just sit there and bounce around and oscillate. Like if you're in a pool, you can create standing waves that don't move. This wave never stands still. It always moves. And he also determined that not only does it always move, if it's traveling through vacuum, where there is nothing else but this wave, it travels at a certain speed he called c. And that turned out to be a very specific value. Essentially 300 million meters per second. And as soon as he discovered this and published it, everyone suddenly realized they were looking at the speed of light. This is exactly the speed of light. And it is a wave that travels through nothingness, just like light does. And that is when everybody realized Maxwell's equations, as they are called, are actually equations not only for electricity and magnetism, they are actually the fundamental equations for light itself. And along with this, what was I going to say? Along with this, they realized that light is an electromagnetic wave. Electromagnetic wave. It literally means that it is a wave of both an electric field and a magnetic field working in harmony to travel magnetic wave. To travel downstream at the speed of light.